Hi viewers, in this particular video we will be discussing a very basic or a very elementary concept in strength of materials called the beam bending. I won't be this is not the kind of video for someone who haven't heard about beam bending before. This is a video intended at those viewers who have seen beam bending before and will be thinking that beam bending is so easy. There is a good amount of chance that you may have missed out a key concept or a key assumption in the theory of beam bending. Often I ask my friends about beam bending, do you know beam bending? And they will be like, yeah, I know beam bending. It is that very simple formula, right? I know Euler-Bernoulli theory and all those stuff, and the formula goes like this: m by I equal to sigma by y equal to E by R. It is this simple formula. So yeah, I know beam theory and it's good. It's very simple. See, there is a lot of assumptions and there are a lot of concepts that goes into this particular formula, and knowing this formula is not good enough unless you understand each of the assumptions that you make before getting here. So let's get started. So that's the whole motive of this particular video, to reinforce the concept of beam bending, or to make sure that we are clearly capturing each and every assumption that forms the pillar for all this kind of formula, so that next time you apply the formula, you know what are the conditions or what are the assumptions that goes into it, what are the conditions where I can apply this particular formula. So let's get started. You know, beam is a structural member where one of the dimensions, let's say as shown in the figure, this particular dimension capital L over here is much higher compared to the in plane dimensions, which is shown as the width and the height of the cross section. So this is just the front view and this is the view which you will get when you look from the side. Good. So going ahead, let me ask you a question. First of all, why is that plane sections should remain plane always? This is one of the first assumptions that you make before you derive beam theory. Why is it? Why plane sections should always remain the same? Sorry, remain plane. So pause the video, think about it, and then come back. I have an answer. So now let's go ahead and look at the answer. See, here I have a simple portion of the beam which is subjected to pure bending. Pure bending means just bending moment, nothing else. I don't have any shear forces, or I don't have any extensional forces or axial forces in this particular beam, just moments. Then let's say let's do a thought experiment. I'm breaking this particular portion into 3 small elements. Now the next thing is obviously to draw the free body diagram. So the 3 free body diagrams will be shown here like this: M, 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 M. So this is a free body diagram. So they are subjected to a same kind of force. Let's say instead of these sections remaining plane, let's assume that they will bulge out. So it's a postulate. We need to prove that that won't happen. So instead of remaining plane, these faces are bulging out like this. What happens if this particular element is behaving in this way? Since the other 2 elements are undergoing the same kind of loading, they should also do the same, or they should also exhibit the same deformation behavior. Having told that, let me draw the deformation behavior for the other 2. It should be also same, isn't it? That the planes are bulging out as shown in a similar manner because the moments are same. Now what happens? Now when I try to bring them together, they are not joining together. There are some voids, isn't it? So if when I move this component over here, let me do that for you. See, when I bring this component over here, then there will be some void, and they won't match together properly. So this is one reason. This particular assumption of plane sections remain plane come from compatibility. What is compatibility? Compatibility, to put it in simple words, that's a condition which tells you the material will be continuous in your domain. There won't be any voids, or that tells you there won't be any gaps inside the continuum of material that you are dealing with. So when your plane sections don't remain plane, then you are violating that. Similarly, let me ask you a question. Is that just sufficient in Euler-Bernoulli theory? Is it just sufficient for the planes to remain plane? Is there any other condition? Often students or even professionals like me, when being into the profession for, let's say, 5, 6, 7 years, we forget that it is not just plane sections remain plane, but they should be also perpendicular to the longitudinal axis. This is very important, because other ways the shear strains comes into picture. This is why you don't have shear strains, because when your plane sections are bending, they are always perpendicular to your longitudinal axis. So this is one reason why we don't talk about shear stresses. So this is one another assumption in the Euler-Bernoulli theory. Now let me ask you a few questions. I have some figures, supporting figures me. So you know the well-known formula of Euler-Bernoulli, that m by I is equal to sigma by y is equal to E by R. So is this particular equation applicable in this scenario as shown here? Here you have a beam. Suppose that I fixed the beam over here. So this is the condition. I have fixed it over here as shown here. So now I'm loading it. Now my question is this particular equation, or which is written over here, this well-known equation, is it applicable in this case? Again, pause the video and come back with an answer. This particular equation is not applicable over here, because as you can see here, the loading plane is not symmetric about the cross section. The cross section, which is kind of an L-shaped, it is not symmetric. The loading plane is not symmetric to the cross section. So your Euler-Bernoulli theorem is not applicable in this scenario. But there are workarounds where you can shift the force to the plane where it is symmetric, and you can do all those stuff, but in its purest form, Euler-Bernoulli theory is not applicable in this case. The next question. I have shown here two cases. The case one, where you have a cantilever beam and a uniform lateral load is applied on it. Okay, and in the next case, the same cantilever beam, you have just an end moment acting on it, end moment. That's it, nothing else. So in which of these conditions you think Euler-Bernoulli theorem will be more applicable, and what is the reason? Pause the video. I hope you got the answer now. The answer is, in the case one, you can see when you take a section, there will be two forces acting on it. There will be the shear force as well as the bending moment. But in case one, if you take any particular section, the bisection, or you can just take a chunk of mass out of it and then draw the free body diagram. So this will be the free body diagram corresponding to case one. Now if I do a similar sort of exercise for the case two, then I will end up with a free body diagram something like this. So in case two, the element is subjected to a pure bending. So yes, it's pure bending, just the bending moment alone. And in this case one, you have both shear forces as well as bending moment. Always keep in mind that Euler-Bernoulli theory, they define this, and this particular formula, they derived it assuming that the element is in pure bending. So in this case, it is not that accurate, but the amount of error is not that much, that I will tell you in a while. So it is more applicable in this particular case. Now let's go ahead. I have another question for you. Again, let me write down that very famous formula, m by I is equal to, sorry, I made a mistake. I'm I'm writing it for, maybe sixth or fifth time in this particular video. M by I equal to sigma by y. I have a simple question for you. I have again a cantilever beam of this particular cross section as shown here. I have some kind of an end moment acting on it. Let me show that end moment over here. So apologies for my poor drawing, but this is the particular end moment acting on that particular cantilever. So my question is, again I have got two cases. I have defined my coordinate system in two different ways. In case 1, I have defined it like this, where my coordinate system is exactly at the center, like as you can see here, it is h by 2 to the top fiber and it is h by 2 to the bottom fiber. In the case 2, it is placed at the CG of the cross section, and so it is far more close to the portion, this particular portion, compared to the top portion. Now my question is, for which of these y's, or for which of this coordinate system is this particular formula applicable? I hope you might have got the answer by now, but always keep in mind that this particular y is only valid when your y coordinate is defined from the CG of the section, or in other words called the neutral axis of the section. Otherwise this formula is not valid. So you should always have your coordinate system defined at the neutral axis. I think so. There were 5 or 6 questions where I asked you a few questions where you can actually cross check, or you can recollect all the concepts and assumptions that you learned as a part of Euler-Bernoulli theory. The last question I have is effects of shear stress negligible in a beam? Because I told you there are certain cases, I told you your Euler-Bernoulli theory is derived from the very assumptions that all elements are in pure bending. But even then, most of the textbooks use Euler-Bernoulli theory. Not just textbooks, you start working in industry as well, they use this Euler-Bernoulli equation left and right in many of the practical scenarios to calculate the stresses due to bending. So why is it? The obvious reason is that effect of shear stress is pretty negligible in a beam. It is not pretty negligible, I would just say it is negligible in a beam compared to the bending stresses. Now can you go ahead and prove it? Hold your thought, I will do that. Just before I go ahead and prove that the shear stresses in a beam are negligible, earlier in this particular video I told you that these plane sections, as shown over here, these plane sections will rotate about the neutral axis and they will be always perpendicular to the longitudinal axis, and this can be attributed as a reason why you don't have, this is the xy plane, I have my x-axis going like this and y-axis like this, then that is one reason why I have my gamma xy is equal to 0. Gamma xy is nothing but the shear strain in that particular plane. So shear strain, from the elementary principles of shear strain, you will have shear strain when, let's assume that this is the initial configuration of an element, and after deformation they are no longer, after the deformation, if they are no longer initially the angle between these two faces, assume that this is a rectangular element and these two edges is 90 degree. Once it deforms, the particular element undergoes no extensional strains, or in other words, the lengths of the 4 sides remain the same, but this angle gets reduced. So that is, this particular angle gets reduced. To be very precise, if gamma is the shear strain, this particular angle is initially pi by 2 or 90 degrees, pi by 2 radian or 90 degrees. It will come down to pi by 2 minus gamma, where gamma is the shear strain. But since we make that assumption, plane sections remain plane and they are perpendicular to the longitudinal axis. See here, if you take this angle, it is 90 degree. This is pretty obvious. This is 90 degree. Now, even the deformed configuration, this is before and this is after the deformation. Even after the deformation, this is 90 degrees because of the inherent assumption that you have taken. So this is one reason why shear strain gamma xy is 0. The final thing that I want to discuss in this particular video is this. Take a canonical example where we have a cantilever beam with a rectangular cross section. The beam is having a length of capital L and the cross section dimensions are B and H respectively, where H is the height and B is the width. The loading for this particular structure is an end load, a point load capital P as shown here, so it is acting. So we know at any particular section, if we take the Freebody diagram, or then there will be two forces. One is the shear force and the other is the bending moment. See, since there is a shear force, it will definitely contribute, or it will definitely cause a shear stress as shown in this particular figure. Don't get too much worried about the directions because it will be taken care by science, so you don't have to worry. This is a common advice which will be applicable when doesn't matter wherever you are dealing with forces. Just don't worry about those directions at this juncture because they will take into account themselves if you use the equations correctly. So here you have shear stresses. I assume that it more or less it acts uniform across the cross section. That's a very crude assumption, but since our objective in this particular segment is to prove that how small or how negligible is shear stress in a bending problem, so I will call this shear stress average. Average shear stress, this will be the force divided by the area, which is P divided by BH. This is a very approximate expression, but for this time being we can live with this. So that's not just the force acting at that particular cross section. There is a moment also, as shown in this diagram. You have a shear force as well as a bending moment. So the shear force will cause you some kind of shear stress that we have already computed. Now going ahead, due to the bending moment, we have shear stress as well. Sorry, we have bending moment will cause a axial stresses or bending stresses as shown in this particular figure. Simple equations using Flexure formula, we have this. This is the Flexure formula. So sigma max will be at the point where the whole cantilever is kind of fixed. So at this point your bending stresses will be maximum. The bending moment acting at this particular section will be capital P times capital L. Very simple strength of materials stuff. Then maximum bending stress will be at the outward fiber, or the fiber which is at the farther distance from the neutral axis. So y max, in this case y max is h by 2. I hope you remember that cross section was rectangular cross section where cross sectional dimensions were b and h. So the maximum value which y can assume is h by 2. Then I, area moment of inertia for a rectangular cross section about this particular axis, about let me highlight that because that's very important when you especially that I value is about this axis because you are bending it about that particular plane. Or so having done that, now it's just plug and chug. All the quantities. Once you plug in, you will get this particular expression for the maximum bending stress, which is shown right over here. Now, in order to compare two quantities, the best thing to do is take the ratio of those two quantities. Now we have average shear stress, which we computed a bit earlier. We have that in the numerator, and then we have our maximum bending stress in the denominator. Again, plug and chug. So once you do all your simplifications, then you end up with a ratio of this kind. So what does this signify? For a beam, in the very first sentence or in the very first minute of this particular video, I told that a beam is a structure where your length dimension is much higher compared to your in plane dimensions like B or H. So mostly for a beams, this particular ratio H by L will be of the order of 0.01 or zero point 0.1. That tells you this ratio will be very small. This particular ratio will be so small, which in turn tells you that compared to the sigma max or the maximum bending stress, your shear stress is so small. For example, if this H by L ratio is around 0.01, then let's say you have a bending stress of 100 MPa acting in your cantilever beam, then the stress due to shear will be less than 1 MPa. It will be nearly 0.5 or 0.6 MPa. So makes sense. So that's why for most of the practical cases we neglect the effect of shear stress. The Flexure formula or Euler-Bernoulli theory is a good assumption. Thanks for watching.